Welcome to this presentation on photochemistry. This is photochemistry first as per the syllabus of BSc third year, fifth semester. This is the outline of this presentation, which includes interaction of radiations with matter, difference between thermal and photochemical processes, laws of photochemistry such as Crother-Strapper's law and Stark-Einstein law. Let us start with introduction first. Photochemistry is the branch of chemistry which mainly concerns with the interactions between matter and light radiations. Or in other words, photochemistry can also be defined as the study of interactions of ultraviolet and visible radiations with matter, resulting into a physical change or a chemical reactions. Now, differences between thermal and photochemical process. On the basis of the source of energy, these processes, reactions can be divided into two types, thermal reactions or photochemical reactions. So, thermal reactions involve absorptions or evolution of heat energy, while photochemical reactions involve absorptions or evolution of light radiations, that is UV or visible radiations. Thermal reactions can take place even in absence of light. Therefore, these reactions are also called as dark reactions. While for photochemical reactions, light is necessary. Hence, these reactions are also called as light reactions. Temperature has significant effect on rate of thermochemical reactions. As studied earlier, the rate of a thermal reaction is directly proportional to temperature. While in photochemical reactions, instead of heat, intensity of light has significant effect on the rate of photochemical reactions. The free energy change, that is delta G, is always negative because majority of thermal reactions are spontaneous reactions, hence decrease in free energy observed. The free energy change delta G may be positive or negative for photochemical reactions. Thermal reaction can be accelerated by the presence of catalyst. In fact, the catalyst increases the rate of the reactions, and this is for thermal reactions. While for photochemical reactions, the rate can be accelerated by the presence of photosensitizer. However, a photosensitizer acts in a different way than a catalyst. Examples: peroxides, various peroxides such as H2O2 hydrogen peroxide, metachloroperbenzoic acids, or benzoyl peroxides, or AIBN. These are some famous photosensitizers used in photochemical reactions. Now, last point is about the example. Majority of the chemical reactions are belonging to this class, that is thermal reactions, such as decomposition of calcium carbonate into calcium oxide and carbon dioxide at high temperature, decomposition of water molecule at high temperature. That is the example of thermal reactions. Now, example of photochemical reactions: photosynthesis, synthesis of vitamin D under the skin on exposure to light; bioluminescence, synthesis of ozone in Earth's stratosphere from photochemical reaction of oxygen; photodegradations and photoalkylation. These are the some examples of photochemical reactions. Now, interactions of radiations with matter. So, how the interactions between radiations and matter takes place, this can be explained with the help of this slide. When light is incident over a substance, then some part of the radiations get back reflected. some part get transmitted, some part of the radiation get absorbed, and remaining part of the radiations get scattered. So these are the some types of response shown by the matter with radiations. Now, significance of photochemistry in understanding the various natural phenomena. So first, photosynthesis. Synthesis of glucose by the green plant with the help of plant pigment chlorophyll, and in presence of light with starting material carbon dioxide and water, there is synthesis of food material, that is glucose. This reaction is called as photosynthesis, and this is the example of photochemical reactions. Synthesis of Next reaction is synthesis of ozone. Synthesis of ozone is also a photochemical reaction. In the Earth's stratosphere, from 3 moles of oxygen, 2 moles of ozones are formed, and that is the photochemical reactions. That is a photochemical reactions. Another is the synthesis of vitamin D. Natural synthesis of vitamin D in sunlight below the skin takes place. That is also the example of photochemical reaction, because from cholesterol there is a synthesis of vitamin D takes place. So starting material is cholesterol, and the final product of this photochemical reaction is vitamin D. Since light is necessary for this reaction, therefore it is called as photochemical reactions or light reactions. Then phototherapy. Phototherapy means the treatment. Example of phototherapy is the treatment of jaundice in newborn babies. So in newborn babies, in many cases, it is observed that the jaundice is the most common disease observed in newborn babies. That is due to the imbalance of liver pigments. So when such babies are exposed to visible light radiations, then the oxidation of that uh, liver pigments takes place, that is bilirubin. So that oxidized form of the pigment get removed from the body through urine, and in this way the excess concentration of these pigments in newborn babies is controlled. That is called as phototherapy. Next phenomenon involving the photochemistry is phototropism. Phototropism means the orientation of the growth of a plant towards the direction of light. Plant in a sunlight show more growth compared to the plant in the shadow. That is the example of phototropism. Photoperiodism is also one of the uh, natural photochemical phenomenon. In photoperiodism, physiological processes such as flowering in the plants is affected by length of exposure to sunlight. That is, blooming in sun power is the example of photoperiodism. Then photodynamics. The treatment of disease with the help of photosensitive drugs is called as photodynamic. And the last phenomenon is bioluminescence. Glowing of fireflies is due to photochemical reactions. That is also one of the photochemical process. Now, next slide is about laws of photochemistry. The branch photochemistry is governed by two important laws, that is, Grothus-Draper's law and Stark-Einstein law. So let us start with first Grothus-Draper's law, or law of photochemical activation, or that is also called as first law of photochemistry. Only the light which is absorbed by a molecule can be effective in producing photochemical changes in the molecule. That is, reflected or transmitted light does not produce any chemical change. Only the light that is absorbed by the molecule can carry out chemical change. And the amount of light absorbed is calculated by subtracting the intensity of initial radiations and intensity of transmitted radiations. That is given by the formula I absorb is equal to I0 minus IT, where I absorb is the intensity of absorbed light radiations, I0 is the intensity of initial radiations, and IT is the intensity of transmitted radiations. Second law of photochemistry is also known as Stark-Einstein law or law of photochemical equivalence. This is a quantitative law. This law gives quantitative information. It states that for each photon of a light absorbed by a chemical system, only one molecule is activated for a photochemical reactions, or one quantum of radiation activates one molecule for a photochemical reactions, and energy absorbed by the molecule is equal to Planck's equations. Therefore, E is equal to h mu, or we can also write E is equal to hc upon lambda, where E is the energy associated with the photon, h is Planck's constant, whose value is 6.626 into 10 raised to minus 34 joule second, or 6.626 into 10 raised to minus 27 earth second. Mu is the frequency, c is the speed of electromagnetic radiation, that is equal to speed of light, and lambda is the wavelength. So for one more, we can write this equation as E is equal to nh mu or nhc upon lambda, that is equal to 1 Einstein, where n is Avogadro's number, that is number of particles present in 1 mole, and this value of Avogadro's number is 6.023 into 10 raised to 23. Now putting all these value in this equation nhc upon lambda, we can calculate the value of 1 Einstein's. So value of 1 Einstein is calculated by putting this value, all these constant value, nhc upon lambda, nhc upon lambda. Only lambda is not known here. N Avogadro's number is known, h Planck's constant is also known, and c speed of light is also known. Therefore, we can calculate here, and after calculation we get this final value, that is energy is equal to 11.96 into 10 raised to minus 5 divided by lambda, that is joule per mole, that is equal to Einstein's. The energy possessed by 1 mole of a substance or the energy absorbed by 1 mole of reacting molecule is called 1 Einstein. Now there are some problems based on these. Calculate energy of radiation with wavelength 1000 angstrom. So here the wavelength of that radiation is given, that is 1000 angstrom, and you are asked to calculate the energy. So we have the equation for the calculation of energy of electromagnetic radiation, that is called as Planck's equation, E is equal to h mu. We can also write h, instead of h mu we can write hc upon lambda, and for n number of 1 mole of a substance, nhc upon lambda is the equation. Now we have all this value with us, Avogadro's number, Planck's constant, speed of electromagnetic radiations, and wavelength. Now putting all these value in this equation, nhc divided by lambda, we get this answer 11.96 into 10 raised to 5 joules per mole. Joules per mole. Okay. Again, second problem. If the value of an Einstein is 72 kilocalorie, calculate the wavelength of the light. So here, the value of E, that is Einstein of energy, is given, and we have to ask, and they have asked to calculate the wavelength. Okay, so here we know the value of En, Avogadro's number, h, c, and E. We just have modified this formula for lambda, and then it become lambda is equal to wavelength, that is lambda is equal to nhc upon E. Now this is the value of En, Avogadro's number, h Planck's constant, c speed of electromagnetic radiations divided by value of Einstein. So 72 kilocalorie is converted into SI system, that is joule. Okay, so multiply it by 4.184, that will give you the value in joule. Okay, into 10 raised to 3 for to convert kilocalorie into calorie. Okay, so we get this value 301.24 into 10 raised to 3 joule. So after solving this, we get final answer 3974 angstrom is the wavelength of that particular light. One more problem is there. It is very much similar to the previous one. Calculate the value of Einstein of energy for radiation of wavelength 4000 angstrom. Again, same formula and same conversion factor is also there. Planck's constant is given already in SI system. Speed of light is meter per second. SI system, convert wavelength angstrom into meter. It will be 4 into 10 raised to minus 7 meter. Now here we have to calculate the value of E. Therefore, E is equal to NHC upon lambda. This is NHC divided by lambda. Now this, after solving, we get this final answer. The value of Einstein is equal to 2.99 into 10 raised to 5 joule per mole, or 0.7146 into 10 raised to 5 calorie per mole, or otherwise we can convert it into kilocalorie, that will be 71.46 kilocalorie per mole. Okay, so all these are the conversions of these Einstein into different units: joule per mole, calorie per mole, and kilocalorie per mole. Now, next point is about the interactions of radiations with matter. When light radiations are allowed to fall on matter, some of the radiations are absorbed, some get reflected, some get transmitted, and some get scattered. In photochemistry, we study the absorptions and emission of light by matter. It consists of the study of various photophysical processes and photochemical processes. Now, the help of these reactions, we can explain what is meant by photophysical process and photochemical process. In photophysical process, there is only physical change, no any chemical transformation is observed. Suppose R is a reactant. After absorbing a light radiation indicated by H mu, it get converted into excited state denoted by R star. During this excited state, it comes to ground state by emitting the light that is absorbed initially. Okay, so at the end of the process we get the same starting material. Therefore, this is a physical process, there is no any chemical reactions takes place. And the example of photophysical processes are fluorescence, phosphorescence, internal conversion, and inter-system crossing. Now, what is chemical reactions? In chemical reactions or in photochemical reactions or in photochemical processes, reactant is converted into product with the help of light radiation. This is indicated here. R is our starting material. By absorbing the radiations denoted by H mu, it gets converted into excited state denoted by R star, and during this excited state, it show the chemical change, it show the chemical reaction, and there is a formation of product denoted by P. So starting material, your starting reactant, and your product have different structure. These two molecules are different, therefore there is a chemical change. Hence, this is a photochemical process or photochemical reactions. So with the help of this tree diagram, we can explain photophysical process. So photophysical processes are divided into two types: non-radiative process and radiative process. So name itself indicate that non-radiative process means there is no emission of radiations during this process, while in radiative process, radiations are emitted. Now, non-radiative processes are of two types: internal conversion and inter-system crossing, while radiative processes are of two types: fluorescence and phosphorescence. So all these phenomenon, the mechanism behind all these phenomenon, such as internal conversion, intersystem crossing, fluorescence and phosphorescence, we will discuss detail while discussing the point Jablonski diagram. That is our second presentation on photochemistry. Now, electronic excitation. What is meant by electronic excitation? So, UV and visible light have sufficient energy, therefore, it can produce a change in electronic energy level, that is called as electronic excitation. This is shown with the help of this diagram. Initially, electron is close to the nucleus, that is a ground state. By absorbing the radiations denoted by the zigzag line, it jumps into the next higher energy state, that is called as excited state. With the help of MOT, molecular orbital theory, excitation of the electron can be explained. This is a typical MOT diagram for the hydrogen. The orbitals shown at the periphery are called as atomic orbital, and orbitals shown at the center are called as molecular orbital. Molecular orbitals results due to the overlapping of atomic orbital. Now, when the electrons are filled in atomic orbital, we have one electron in both the hydrogen atoms, and after overlapping of atomic orbital, we get two paired electron in this uh, lower uh, uh, molecular orbital. Okay, so the molecular orbital, these two molecular orbital, one of the orbital that we call as highest occupied molecular orbital denoted by sigma 1s, and this sigma star 1s is lowest unoccupied molecular orbital. Now, what happened by absorbing the radiations? Electron from HOMO jumps into LUMO. The jumps of so this process of shifting of electron from HOMO to LUMO is called as electronic excitations. Now, excited state is of two types. Generally, in excited state, we have unpaired electron, but if both the electrons they get oriented in same direction, then that is called as triplet state. And if the orientation of electron, spin of the electron is opposite, then it is called as singleted excited state. So singlet excited state is denoted by S1, in which the spin of the electron is opposite, while triplet excited state is shown by T1, where the spin of the electron is same, and the multiplicity is calculated by the formula 2s plus 1, where s is equal to electron spin. So in singlet excited state, spin is 0, therefore the value of 2s plus 1 is 1, and that is singlet. While triplet, spin is 1, that is 1 half plus 1 half. In triplet we have the value of s is 1, therefore 2s plus 1 is equal to 3, and that is why it is denoted by T state or triplet state. A triplet state is more stable than singlet states because in triplet states electrons are unpaired, lesser interelectronic repulsion takes place, while in singlet state electrons are pair, causing interelectronic repulsion and is unstable. Now for electronic excitations, we have selection rule. We have two rules, spin selection rule and Laporte selection rule. In this topic, we will deal with only spin selection rule. And spin selection rule for electronic excitation is delta S is equal to 0. Then it is allowed. That is, transition without change in multiplicities are allowed transition, while transition with change in multiplicities are not allowed, are forbidden, or rarely observed. So excitation from ground state S0 to S1, first excited state, or from S1 to S2, that is excitation of electron from first excited state, singlet excited state to singlet excited state second, S2, or S2 to S1. All these are allowed transition because during this transition the multiplicity does not changes, while direct excitation of electron from ground state to triplet state is forbidden because during this excitation multiplicity of the electron changes, that is singlet to triplet. This singlet and triplet are called as multiplicities. So since there is change in multiplicity, This transition is forbidden, that is, rarely occur, rarely observed. Now, chemical bond energy is of the order 100 to 1000 kilojoule per mole, and the energy associated with UV and visible radiation is of the order 150 to 600 kilojoule per mole. Therefore, light radiation have sufficient energy to break the chemical bond, and hence they can able to carry out chemical reactions. So this is for photochemistry first. In our next presentation, we will discuss some advanced part regarding this photochemistry. Thank you.